Okay, so my name is Koen Bertels. I'm the founder of QBee. I've been for 20 years a full professor in Delft University of Technology in the Netherlands. And now I'm part-time professor in Ghent, but I'm basically busy with the quantum genome sequencing, but quantum algorithms in general within QBee with several of my colleagues. So what is genome sequencing all about? Everything in medication, in the medicine field, or in the biomedical field, so the pharmaceutical industry, is based on DNA. Now, another company I created several years ago was actually sold to Illumina, which is the largest DNA company in the world. And they decided that the software implementation that we did was very efficient and now is part of, let's say, the Illumina machine that anywhere in Europe, United States, or in other places in the world is being used. Back then, I wanted to have also FPGA accelerators, but I had also a very good CEO back then, and he said nobody even knows what FPGAs are, so we'll not do that right now. Yeah, but now when you go to any data center in the world, you get access to, let's say, FPGAs. That's a separate story. So what is the core idea of genome sequencing? Is that the human genome or any living organism DNA is made out of, let's say, around 1.5 billion kind of characters, 4 characters only. Yeah, but that is in this, we get short reads from these Illumina machines, and then the QBee software, and now it's of course Illumina software, yeah, maps this short read onto the reference genome. So back then, and I'm talking about 15, 16 years ago when QBee was created, yeah, it took around 7 days, and then we substantially improved the implementation. So from 7 days, it now takes about 1 day for a single DNA genome sequencing. Okay, so that is the core idea. So now I created company number 3, QBee. Yeah, I like the name B in a company name. Yeah, and the goal is again to work on many topics, but why not genome sequencing again and make a quantum version of that? And our long-term goal is to go from 1 day to an individual DNA analysis. Yeah, about a couple of minutes. Let's say 1 minute. Yeah, that is the goal. The entire pharmaceutical industry is looking at that. Any medical training you will follow wherever in the world is also based on the DNA profile of people. So let's assume at some point we will have a device like what you see here, where you can put in your finger and then a couple of minutes later, it spits out your genome analysis, your DNA analysis. It's also relevant for Mars because the goal of, let's say, NASA and ESA, yeah, is to send astronauts to Mars. That's a flight that by rocket that takes about 7 to 8 months. And the goal is that they would live the rest of their lives on Mars. Now, just that you know that a simple sound message is going, it takes 20 minutes to go from Mars to the planet Earth or vice versa. So that's already 20 minutes at the speed of light. Now, what do you want to do if you have a serious you need medical support? Yeah, you need to do that also on Mars itself. So that is also, let's say, the second benefit of our genome sequencing, the quantum version of these things. So I gave similar talks in Australia, where my son lives and works. Yeah, but actually during that week, the 2 or 3 weeks I was there was also an article on Mars where they mentioned indeed the genome sequencing, yeah, for a life on Mars. I will not go into the details of what genome sequencing is all about, but I will simply indicate a lot of these things are simply classical algorithms. So it's always a hybrid way of developing applications. And you see here again the quantum way. These are the quantum operations where we use superposition and those kinds of things. Yeah, and simply interpret maybe this little table here, because it's a substantially reduced thing. I will come back to that later. Yeah, but if you have 2 yellow signals, that means there's a perfect match for the short read here. If there's two gray ones, yeah, like we see here, or a single gray one, then we have partial matches. And the goal is, of course, that we want to have, let's say, the best match possible for any short read on the reference genome. Yeah. So just know that for any living organism on this planet was 1.5 billion CATGs. Yeah, and the short reads, we try to lengthen the short reads. So the bigger it is, the less we need to fix it. Yeah, or the mapping goes faster, should go faster. Yeah, but now we in our approach, yeah, based on the PISC methodology that I will not explain right now, we have to substantially reduce it, because what is important now is to have a functionally correct kind of evolution of the different quantum gates that we need. Why is it important? Well, because we only have right now around 20 quantum gates. And if you're using most likely a laptop to look at this video, yeah, this laptop or a personal computer has, let's say, around 10,000 electronic gates. Yeah, so compare that to the 20 gates that we have to versus several thousands. Yeah, we still have a long way to go in the quantum world. And that is the main goal of QBee. Yeah, so whenever we develop new algorithms, we will for sure discover new quantum gates, like what Aritra did also for his PhD, and he's a partner in QBee, by the way. Yeah, so that needs to be translated into the universal gate set that we have. Yeah, and so that is the goal. But if we discover new quantum gates, yeah, it's also the goal to build a company, to get money out of it. So that's why we need intellectual property of these things, and that is also something we take care of in Leuven. So let's simply assume again we have a very short reference genome, and we have also very short reads. Yeah, and this is again the ATC/ATG is translated in these colors, so you can easily map it again in the colors. Yeah, this particular kind of genome sequencing. So let's assume that we're looking for GC, so that's yellow and green. Oh, we only have one of those things that's on this particular location. So that is basically what we want to be doing. We have a lot of short reads, and we need to map that into the reference genome. So this is just a compiled slide that I'm showing, yeah, where we're looking indeed at this particular 6 and 7, so TA, yeah, and so we see that this is the place where we find it, and these are actually numbers running out of the Qiskit simulator, yeah, which you can download for free from the internet. Yeah, you don't yet have, well, there actually is a free version of this PISC kind of implementation. Yeah, but what is important to see is that even IBM is now also supporting perfect qubits, just like QBee is doing. And this is really the message that we're bringing to the world, to the community. Yeah, when we are developing new algorithms, first formulate them using perfect qubits, so you abstract away from all of the problems that quantum physics chips will still have. Yeah, and you will see that indeed the size and the speed is similar to each other. Yeah, and so but what is very good to see is that the IBM and the QBee matches are indeed exact. Yeah, so this is important. We want to have the functionality which is mathematically correct, specific kind of mathematics. That is true. I will not go into those details. Yeah, but let's now simply go again and do a simple genome sequencing kind of thing. So now I connect to the computer in Leuven. So I'm in Antwerp, and now I connect to Leuven. And I did something similar when I was in Sydney. Yeah, and so I'm gonna Python. I'm gonna launch the language, and then the genome sequencing kind of algorithm as we implemented it is gonna ask, "Are you in the office or not?" No, I'm not in the office. Yeah, and then I'm gonna say I'm looking for, let's say, the TC. Yeah, kind of a combination. Yeah, I press enter, it executes on the machine in Leuven and already sends back the result. In Sydney, I had a similar kind of performance. Of course, the transportation takes a couple of seconds longer, but still, this is where we have the solution. So you see here the TC, that is indeed where at this location where we see it, and that is indeed what result we get back. Yeah, you see again the difference between what the superconducting qubits is reporting, and this is not a blame to IBM. This is simply showing that we can have any kind of qubit technology, being ion traps, semiconducting, superconducting, photonics, whatever it is. Yeah, it will always be error. There will always be errors. Yeah, it's only when you use perfect qubits that mathematically, yeah, and functionally you get correct results. And this is very important to show and to understand. So this is basically the short message that I wanted to bring with this presentation. Thank you very much.